Emission there, supervised by Colin and Talby, and she's going to tell us about all the work we've been doing in Spider. So, over to you.
Thanks. So today I'm going to talk about work I've been doing for my PhD. The main focus has been on mapping the Spider experiment. I'll just give a brief overview of that pipeline, and then the main thing I'll talk about is modelling polarized foregrounds. So we've been modelling for a thermal dust emission and synchrotron radiation and contribution to CMB experiments that we've had. So this work is done with Galactic and Imperial College, and foreground modelling is done with Karim Talish and Daniel Day, who was previous postdoc of Harvard. So in the beginning of the talk, I'll just outline the status of the Spider experiment before moving on to go over the foreground modelling. So I'll be talking about which foregrounds go into the model, which foregrounds are important to model, how do we actually model the galactic magnetic field and the emission through it, and then I'll compare the model with WMAP and CMC data, and then at the end I'll conclude with some possible uses of the model and what kind of thing it can be used for. So firstly, just a brief motivation, which everyone will already know. So if we decompose the FRW metric in the SPT decomposition, so we have scalar perturbations, which come from density perturbations in the early universe, and these produce an E-mode type polarization of the CMB. However, tensor perturbations produce both E-modes and B-modes, and tensor perturbations are from gravitational waves. And on large scales, a B-mode signal is only produced by a primordial gravitational wave background. So detection of B-modes on large angular scales will give us insight into primordial tensor fluctuations, and will be a signature of a key signature of an inflationary epoch. So through these experiments, we hope to measure the ratio of tensor to scalar power spectra, and through this we'll have insight into the energy scale of inflation. So there are many experiments that have been targeted polarization of the CMB. So the E-mode has been detected. It was first detected by Daisy in 2002 and was subsequently confirmed by these other experiments here. B-mode hasn't yet been detected, but we have upper limits on the power spectrum. And there are many experiments targeting this, and here's an overview of them. So we've got HIVE, which will measure full sky, give us very good constraints on the galactic magnetic field next year. And then we have various ground-based experiments, such as at Pole, over there in Earth, and at South Pole we have, in Antarctica we have FGPol and ice arrays. We also have various balloon-based experiments. EVEX is going to launch this year, and SPIDER will launch next year from the McMurdo in Antarctica. So this is the current status of, this figure was produced a few years ago, showing the current 2 sigma detections from these experiments in the spots here. So you can see that the upper limits we currently have on the B-mode power spectrum, shown against theoretical around the CDM power spectrum with R of 0.1. And just an example, summary of the challenge we face, polarization is an order of magnitude below temperature and varies between 1 to 10% across the sky. So what is SPIDER? It's a long duration balloon flight, which will fly for about 20 days next November. These are all the institutions involved in fabricating detectors, making the gondola, and analysing data. And so it will fly at an altitude of 36,000 meters from McMurdo on the coast of Antarctica. This is the observing region that we'll be targeting in white. And this comes from a paper by Fraser's Howe a few years ago. On the left we have the IRS satellite data, 100 micrometers, and on the right we have WMAP temperature data at 94 gigahz. So you can see that in the spider region, it's relatively clear of foregrounds in both maps. And an analysis was done of 2% disk to the sky to look at the region of minimum foreground contamination. And you can see that region in the black circle here. So it's contained within the spider patch. And this was the boomerang patch, and this is the bicep patch for comparison. So the spider is designed to target the approximately have maximum sensitivity at L of 80, and will measure in this L range 10 to 300, and it will be sensitive to our 0.03 at 3 sigma. However, we also have funding for a second flight, so there's a possibility for a decrease in this. And then we'll be measuring about 10% of the sky with 3 frequency bands, so 90, 150, and 280. In this table here, you can see the number of detectors per focal plane unit, and there'll be 2 detectors at each frequency band. The beam size is less than a degree, so at 150, beam is half a degree. I wanted to give some idea of the scale of the increase in the size of data sets for CMB experiments. So here's just some examples I pulled out to show that. So Boomerang had 16 detectors mapping between 0.22 and 2% of the sky. WMAP had between 2 and 8 waveometers in several frequency bands measuring the whole sky. And Black has 52 detectors. However, Spider will have 512 detectors in two focal points per frequency band and measure about 10% of the sky. So it's a massive increase in the size of data to be analysed. And some examples of other experiments are Galactic and Bicep, which are also very large arrays. This figure here was from a few years ago, showing the size of the increase in the size of data sets, so normalised to the Boomerang 98 data set. And above this line are projections for future experiments. So you can see that Spider is going to produce more, about 5 times more data than Black. I think Keck has moved up in this whole plot. And the map making problem is outlined on this slide. So we're aiming to solve for a sky map X given the time stream D from 500 detectors per focal plane. So here X are these Stokes parameters, IQ and U. And this is essentially a linear algebra system where we have this Rose equation. So A is a pointing matrix which scans the sky map B into a time stream D. And in addition, we have a noise vector N, where N includes the correlations between your detectors and noise, detector noise and other noise. So as you can see, there are going to be several thousand time streams from each one from each detector. And in order to analyze this, we must use parallel processing. So Spider, we've been coming up with a parallelism in MPI, and we've called it SpinP. So MPI is a fast, scalable way of writing high-performance parallel computing codes. So we need an optimal solution for the map given the detector time streams. So we solve this using a linear estimator given by W. And W has this form here. So if you act with this on a time stream, you inverse noise weight the time stream, then you project the time stream into a map, and then you multiply it by this inverse matrix here, where N is your noise covariance matrix. So this amounts to scanning, inverse of this inverse is of order n number of pixels cubed. So it's computationally very
So the n
intensive.
pixel is tiny, right? You're looking at an L of 80, so you have at most 80 squared independent with freedom on the sky, and only a few thousands.
So the number of pixels is ordered 10,000.
Yeah, and on the laptop would take a second or millisecond maybe.
But this matrix here isn't a sparse matrix.
Understood, but then, Q, for example, was matrices with 100,000 elements.
The 10,000 takes more than a second, but it takes, you can do 10,000.
And you're analyzing a few thousand time streams, and you have to account for all the detected correlations.
And I would have thought that n inverse could be expensive, an ATN, but the n pix cubed I would have thought is the least of all issues. I would have thought all the expensive stuff comes in computing n inverse A. That could be expensive because that n time stream is big, but n pix is small, right?
Yeah. Okay, yeah. So the algorithm that we've chosen to solve this problem is the conjugate gradient method. So what we do is, instead of solving for the sky map x, we solve for a stripes map y, where you subtracted PD, where P is a pixel hit counter, so it's the number of times your certain pixel is observed. So y is a combined stripes map, which is summed across all detectors every iteration to have, so that you have the current iteration of the stripes map. So the stripes map y obeys this equation here, which is of the form my equals b, which we can then input into our PCG method. And y now depends on only the scan strategy and the noise characteristics of the noise covariance matrix. And just briefly, what a PCG method does is it's similar to a CITA method. So you form a quadratic given by this combination, and then its derivative is given by my minus b. So if you minimize g, that amounts to solving your original linear system. So the analysis pipeline that we're developing does these steps. So you generate your time streams from simulating maps, and these simulated maps are being convolved with the beam and the detector pointing, and so you scan them with your detector pointing. And you've included noise, which you generate in chunks, where the noise is over length of time, where the noise is stationary. So you generate many time streams from these simulated maps. At the moment, we're testing on subsets of about 40 detectors, and from about 4 days of data. So this has to be scaled to 20 days with 500 detectors in the near future.
So 4 days, the time scale in which you consider a block of data to be independent, like you don't consider correlations outside of 4 days? Or?
No, there are definitely, within the 4-day chunk, there are lots of chunks where the noise is stationary.
Okay, so what's the period of like what's the time scale that you chunk the data at?
I think so whenever the telescope scans across the sky and then changes direction, the pixels will be flagged, so the chunks are of the order of an hour, or maybe it's more than that. I'm not really sure, but quite small.
And at what rate do you plan to digitize the data?
The current estimate I'm working for is 400 hertz, but I think there'll be an update, so it might be a bit less.
So why isn't that equivalent to the saying you take an ounce of data, make a map out of every ounce, and then stack the maps, and then you would never pay, then you never have to look at any big matrix. because the only reason you need to have this big n, the only reason you have to worry about this n being some gigantic matrix is if you worry about correlations between data from today and tomorrow. If that were an issue, this could be very, very expensive because you have to invert some correlation between very long time scales. But if you're going to cut out all correlations longer than a few hours, that means my n is block diagonal.
I don't think you're cutting out correlations on time scale. And to fully measure angles in Q and U so you can recover the Q and U match, you need to have about 4 days of data.
Understood to make the full complete map, but the expensive part is when n gets large, it's expensive, but your n is block diagonal, meaning the n inverse you can just inverse each block, so it's only really a few hours in the n dimension that you have to worry about. I mean, the data is correlated, but the data is small, the data is small anyways, there's not that many pixels. I just want to understand where the computational challenge comes. In a naive level, it's like completely parallelizable. Every scan goes to a different computer, embarrassingly parallel, and then you get a bunch of model-sized matrices and add them up, and you're done. And you don't have to even the API, you just run.
Well, the correlations are of the scale of you have noise drifts across the scan region, and the scan is about a. So you have these drifts in the noise. So I don't think it's block diagonal on an hour.
Okay, I misunderstood what you. Maybe we should talk a little offline, because I thought what you just told you is that you only consider correlations up to.
No, I'm not sure if that's. I can't remember the exact numbers, so maybe go over it later. So then we calculate the naive map, which is just a naive binning of the time stream into each pixel and dividing by the number of times you observe that pixel. And so then you solve for y using your PCG method until you've reached a given tolerance. And then your final sky map is just the sum of the naive map and the stripes map, where the stripes map includes all the noise from the scan strategy and detector correlations. So the current status of the map maker is that we have convergence for IQ and U. However, at the moment we're implementing systematics testing into time-ordered data in order to calculate residual power spectra from the injected systematics. What we'll be doing is testing on full flights of 20 days across full focal planes, which we'll use a cluster. And we'll be injecting detector correlations into the time-ordered data. And also we have to implement the calculation of the pixel covariance matrix and store it in this matrix. And we can make use of existing work from the boomerang pipeline on this, so it's not as far away from being ready as it would seem. So that's all that I'm going to go over with regards to the map making status. So now I'll talk about
Again, the map maker. So you make independent. You have various polarization states that you measure, and then you make 4 Stokes maps. IQV. That's the concepts.
So yeah, you have 3. You have the IQV Stokes maps from in the final solution map.
So when you say map, you mean the 3 maps of IQ.
Yeah, I mean a vector of IQ
and U. And those maps, you don't have to worry about, like say, if you have an array of squints between the pixels such that they actually are non-locally entangled, so you worry about such issues?
Do you mean each detector scanning a different patch?
No, that each detector has a different position-dependent polarization leakage. This is generally called squints, right? That's the 2 polarization states are non-trivially entangled.
So each detector has an estimate of the polarization leakage which comes into the time stream D. So it's a multiplicative factor in front of the Q&E. And that's how we done per detector.
But you do the time stream. So if it's a non-local correlation, then you can't think it anymore, I suppose.
Must have been to the
projection matrix, right?
Well, that's a question, right? So if your projection matrix, so your A matrix, is it just a pointing matrix? It's like just a matrix of permutations of, you know, a pixel on the sky to a pixel in your time stream, or is it a non-local convolution that can correlate?
Does A have information with it?
Yeah, at the moment I'm not including that, but it will in the end. So A will be a convolution of a beam. So there'll be multiple hits per row of A.
And are they planning on measuring the beam? Do you do that live, or do you do that in the lab? Like, do you do that in flight?
I think that's under the full flight.
Is that?
I think they measure the beam. Okay, so now I'll move on to the model for polarized foregrounds. So these are important as they may dominate at all frequencies being looked at by the next generation of experiments. So the dominant foregrounds are synchrotron radiation, which dominates below 100 gigahertz. And this is due to acceleration of cosmic ray electrons in the galactic magnetic field. And then we also have above 100 gigahertz, we have thermal radiation from dust grains, which dominates. And this is due to dust grains being non-spherical and emitting light polarized along their longest axis. There are several other foregrounds, free and spinning dust. However, these have been shown to have a low polarization fraction in various studies. So we don't include them in our foreground modeling. And this figure from a few years ago from the WMAP team just shows the frequency dependence of synchrotron and dust in antenna temperature compared to the expected CMB anisotropy. And you can see that in intensity that's the minimum here.
You're a much higher frequency.
Yeah, 90 and 150. So we're going to be mainly concerned with dust.
So, so you said that the polarization of spin dust is very low, right? But I remember that observation by Massillari and Dickinson. They show the average is the 2%.
Yeah, they show that.
The upper limit we found is like 5 or 6%, but the average is 2 or 3%. But if you compare with the correlation of CMB below, it's still much higher.
So there have been studies done by Untitled Chapter which show that if your model doesn't include spinning dust or free, but it's present in the data, then it only biases your estimates are by about 1%. So yeah, these studies show a few percent polarization fraction, but we think that it's negligible. So why do we need these foreground templates? So future experiments such as Planck will provide very accurate tests of the galactic magnetic field model, and models such as this could be used to constrain the large-scale parameters of the galactic magnetic field. However, there are several alternative models. So there was a model by Fose et al. A few years ago, and the Fire Sky model has just been released, or a paper describing it has just been released. And hopefully these models will be used to constrain parameters of the galactic magnetic field. However, they could also be used to test component separation methods. And we also hope to use these templates to look at foreground contamination in patches being targeted by suborbital experiments. Now, the key features of the model are that we have a purely internal model of polarization degree and direction. So we have maps of these across the sky from the internal galactic magnetic field model. The other component of the model is then from external templates, so total intensity information and frequency dependence. This information comes from data that we have currently. So, for example, for the dust templates, we use the FDS extrapolations of IRS satellite data. So, the current lack of data on the polarization is really why modeling this is important. So for dust, WMAP and the IRIS satellite have matched the intensity of dust emission, but polarization is very poorly constrained, and there is some measurements by, for example, Argyos and Bicep close to the galactic plane, but there's little data at higher galactic latitude. And then for synchrotron, WMAP measured polarization and intensity at 23 gigahertz, and intensity was also mapped by the Haslam All-Sky survey at 408 megahertz. So this kind of shows the importance of modelling given the lack of data, although more data will be coming very soon. And we've put templates on this website here from the dust model, and the synchrotron templates will be uploaded shortly for download. So there are 5 main components which go into the modelling. So we generate a 3D model of the galactic magnetic field and a 3D model of the dust and cosmic ray electron densities. And then you integrate this model out along lines of sight to each pixel in the sky to obtain Stokes parameter mass. Now the magnetic field has 2 approximately independent components. There's the large-scale field from the galactic magnetic field, and there's a small-scale turbulent field from turbulence in the interstellar plasma. And these have approximately equal RMS values. There's also the large-scale dust or cosmic ray energy electron density distributions which need to go into the model. And then details of how the grains align with the galactic magnetic field, or the direction that synchrotron radiation is emitted, and then how this emission depends on magnetic field strength. So briefly, for the dust case, dust aligns with its axis parallel to perpendicular to the galactic magnetic field, and then it preferentially emits light polarized along this axis, so you have a net linear polarization. Also, what needs to go into the model is information on the dust, how many dust populations there are, for example, and the frequency dependence of the emission. And this comes in through the external templates. So for dust, we use the FDS template intensity map extrapolated to the frequencies we're observing at. So this model used IRS satellite data from 100 micrometers and 240 micrometers and extrapolated it to microwave wavelengths. And it's been shown that it agrees very well with WMAP in terms of morphology, but some differences in the amplitude. In the case of the synchrotron radiation, we take the Haslam 408 megahertz data and extrapolate it with a constant spectral index across the sky. And for synchrotron, the emission is also perpendicular to the galactic magnetic field. So for these templates, there's been studies showing that synchrotron radiation, the spectral index varies across the sky, and also there's a steepening with frequency. So there are differences between extrapolating the Haslam map to 23 gigahertz. There are differences with the WMAP 23 gigahertz data. However, for our model, we can use other templates in the model based on current information on which data sets are more
It's almost very secretive. I think almost everybody in Spider has access to Planck data, which is just cleaned up all of these, right? So is there any, so you have
Planck data or the PSM?
The Planck data, isn't the Planck data cover exactly the band you want with the exact same polarization properties? So don't you have a perfect template?
I don't.
Well, everybody other than you on the team does. Right? So.
I'm not sure if they do have access to Planck data. We've got access to PSM data now. I don't think they do. I don't.
I think you should try to dig maps.
Great.
Okay. Wait 1 more month, right?
No correlation with the least until
Hold your breath.
Okay, so there's also the details of the large scale magnetic field and the distribution of dust and cosmic ray density. So these two figures here show two popular magnetic field models. On the left is the isometric spiral model, and on the right is the logarithmic spiral model. And you can see quite big differences between the two in terms of modulation of the field in the spiral arms of the galaxy, which this one attempts to model. And in the LSA you can see no azimuthal dependence of the field. And this green dot here is the position of the sun. So you can see you're looking into the center, through the center of the galaxy, and on the side you'll have contributions from all these variation of magnetic field amplitude. And in red here is the dust density contours, stepped in contours of 0.1, normalized to 1 at center. So you can see that by the position of the sun, the dust density has dropped off massively. And this is what we use to model the dust density. This distance here to the sun is 8 kiloparsecs, and the radial scale of the dust is modeled as 3 kiloparsecs with a scale height of 200 parsecs. And for the cosmic ray electron density field, this is slightly different. So the radial scale is 5 kiloparsecs and the scale height is 1 kiloparsec. However, it has the same form as this. So on small scales, you have the second contribution to the magnetic field, and this is from turbulent motion, and it's been shown that on scales less than 100 parsecs, it's consistent with a Kolmogorov turbulent power spectrum. So this Kolmogorov spectrum has this form here. So for a 1D realization of this spectrum along the line of sight, you have a -5/3 slope to the power spectrum. For a 3D realization, you'll have a -11/3 slope. And we can model this turbulent field on 3D for small patches of the stars, which will then include spatial correlations. So a Kolmogorov spectrum has a characteristic energy injection scale, which we set at 100 parsecs, and then a turbulence cascade from largest small vortices. And then there's a dissipation scale, which we set to be negligibly small, but small compared to the resolution of the model. And these small scales become important about an angular size of 1 degree. So below these scales, our model is purely statistical, coming from this statistical realization of this power spectrum. So a Monte Carlo approach could be used for more realistic estimates of on smaller patches of sky.
General question: do you have a sense for any one pixel, the extent to which discrete objects, supernova remnants, etc., are contributing to polarization, the fraction of the polarization that's by discrete objects that might be evolved on short time scales?
I think compared to the diffuse emission, it's very small. I don't know exactly the number.
But there's a trade-off between the accuracy of which you know the foreground and the proportional contribution of those discrete objects.
So I don't really know. So for the thermal dust emission, then the observed polarization that we measure is the sum of many independent regions along each line of sight. So it includes variation in all the 3D structure along the line of sight, as well as varying across the sky. So the polarization fraction that we observe is less than the intrinsic polarization fraction at emission due to depolarization along the lines of sight, due to the variation in the magnetic field direction. So for the Stokes parameters IQ and U, we then integrate through this magnetic field model. So to I, you integrate the dust density along the line of sight, and epsilon gives the emission strength of the dust at a frequency nu. However, for Q and U, you have to include the magnetic field strength, and we assume that it depends quadratically on the magnetic field strength. You also have a normalization factor here, which is put in by hand to match the current data. So we can set this to match 3.6% polarization fraction outside the PO6 mask. And then for this case of synchrotron radiation, the line of sight, the IQ and U integrals are quite similar. However, in this case, you have the cosmic ray electron density here, and different dependence on the magnetic field strength. And R max is set to 30,000 parsecs, so much greater size of the galaxy. And then.
So earlier on, you mentioned that you include the details of the radial element in the model. But from the Q and U parameters here, I don't see the parameter for the radial element. It's likely that you assume perfect parameter.
Yeah, we're assuming that the magnetic field, that the dust is aligned perpendicularly to the magnetic field. So we don't include misalignment of dust with the magnetic field.
3%. The previous slide, the little p zero was, is that 3%?
Yeah, that's to overcome the polarization fraction that we're talking about.
But it's like a correction factor. It's not from the field observed or not from the computation. This P0 is not just the factor you add to adjust.
Yeah, we set it to match the WMAP polarization function. So it can be rescaled to match any value. So here for synchrotron, this normalization P is 0.75. This comes from the spectrum of the energy distribution of cosmic ray electrons, which is proportional to e to the minus s. However, due to line of sight depolarization, this polarization fraction is decreased massively, depending on which line of sight you're looking at. So then from these this internal model of the IQ and U Stokes parameters, we can form the polar map of the polarization degree and angle. However, to include the observed small-scale structure, we then have to scale this by the external intensity templates. So what we do is, for intensity, our model it comes from the external templates, and for Q and U, the predicted the templates have this normalization here where you multiply by the Haslam template, multiplied by the polarization fraction and including the angle. So here it's either the Haslam data extrapolated to the frequency that you're looking at, or the FGS template for the dust case. So here's what the dust templates look like. On the left we have the bisymmetric spiral model, and on the right we have the LSA model, and here's Q and U. So you can see that the galactic magnetic field model that you choose makes a big difference in the observed emission, especially in the galactic plane. So this is one possible use of the model in constraining magnetic field models. For synchrotron here, I've plotted our model on the left and WMAP 23 GHz data on the right. And again, this is Q and U. So you can see that at 23 gigahertz, the large scale, on large scales, the model reproduces very well the observed structure in WMAP data. However, on small scales, you see noise, which is partly due to residuals in WMAP data. And the units here are antenna temperature with a maximum of 18 microkelvin. And here we've fixed on the logarithmic spiral arm model because this is what is used by the WMAP team in their analysis. So here I've plotted the polarization amplitude and angle coming from the model of Synchrotron Emission. So again, on the right we have WMAP 23 gigahertz data. So polarization amplitude, again on large scales you see light blue green with WMAP data, but there are slight differences, for example in the north sphere, which are possibly due to differences in the extrapolation of the Haslam data to 23 gigahertz, which leads to differences in amplitude in regions around the galactic plane.
Can you just explain the basic thing on what basically is limiting the angular resolution of your polarization model? Since you're not attempting to give yourself fine details there,
so
you can see in the WMAP.
The angular scale of the Haslam maps is 0.85 degrees, and then the line of sight resolution, so we integrate through this 3D model of the turbulence, small scale turbulence field at a resolution of n side field pix resolution at 128. So yeah, these maps are from this line of sight resolution at n side 128. But if I plotted it with templates generated with like high resolution, you would see fineness structure. But I think the main difference on less than a degree is possibly residual noise in the WMAP and CMC templates.
I guess the basic question though is that if you had improved map workflow to start off with, what would be really limiting the accuracy of your model? Right?
Yeah, it would be the angular resolution of the intensity template.
But I mean, that brings us to line of sight averaging.
So the resolution of the line of sight interval is 0.1 parsecs. So that could be decreased, and then it takes longer to generate a template.
The white panel is the WMAP 7 actual data, or what is that?
This is WMAP NCMC templates. So this comes from an NCMC fitting onto the WMAP frequency band.
WMAP 7?
Yes, sorry. So again, for polarization angle, you see very good large-scale agreement with WMAP NCMC data. And I should say that the polarization angle comes purely from the internal galactic magnetic field model. So in the angle, you're not seeing any contribution from the external intensity template here. So this is purely the prediction from the internal model.
How much does that vary if you switch to the other field?
So it kind of shifts. You can see that this is shifted on the galactic plane. So if you use the other one, it would be more symmetric. So now I'm going to look at the comparison with Planck sky model. So this was just released, and we're planning to do a more in-depth comparison. The PSM uses WMAP 23 gigahertz data, and then on scales of less than 3 degrees, this is modified by multiplying by normalized Gaussian random fields. So you see very good agreement with, obviously, with WMAP and polarization data. So in a future work, we're going to look at comparisons with this. So what we've also done is calculate foreground fits from the model. So what we did is, we fit the power spectrum for a power law in L plus the white noise component here. So A is the amplitude and the foreground component, and there's the index and N is the noise amplitude. So this is along the same lines as the analysis WMAP team did. We include corrections due to the F-sky effects and pixel beam smoothing. And when we perform the split on the power spectrum of the model, we come up with very good agreement with the WMAP data in the synchrotron case. However, in the dust case, we have quite a big difference in terms of the amplitude and the slope of the power. And visually, this is the difference that we see. So the synchrotron case, you can see quite good agreement in terms of amplitude and index. And in the dust case, you can see quite a big difference. And I think this is due to residual noise in the MCMC templates. So then we also look at the correlation between our model and
residual noise in MCMC template on the dust map. The WMAP dust map is all just regenerate the polarization of the template. So it just says that the assumption that those guys made in the model, it's just a ad hoc. If you understand this right, so the WMAP model is just invented by someone, say Loja, for example.
I think that
you invent somebody and you're saying you two inventions are just not agreeing, right? That's what you're saying. Nothing to do with data in this case.
yeah, sure.
Well,
But
I think that's what you mean. Like, the template is constructed out of FGPs, and then we just sort of have magic and sprinkle the coordination, which we do with Starbucks.
Yes, but she now has a different amplitude and different spectral index in that last plot. And then we're supposed to read into it that you guys already know the spectral index of polarization and therefore there is a disagreement, or is it just saying that it was invented and therefore it doesn't matter? Okay, that's fine. Sounds like the discrepancy may not matter, right?
because it's just due to the
Because
difference in
that's
models.
not invention here, that's somebody's invention. We are not invented in the words.
I think for dust, the MCMC templates from WMAP that high galactic latitude are dominated by residual noise. So that was what I was saying for the difference between the model and WMAP. Anyway, I'll go on to explain. We look at the correlation between the model and WMAP by calculating this correlation with coefficient R. So we perform a galactic latitude cut from 0 up to 80. And we look at Q and U. Q is red and dashed line is U. And up here we have the synchrotron model. So you can see quite a high correlation between the WMAP and the synchrotron model and our model. And for the dust case, you see at low galactic latitudes quite a big quite a drop in the correlation. So these were calculated from maps smoothed with a quite large beam, so that you're not seeing effects due to the small scale residual noise. However, for the dust case, this is showing that there are big differences between the model and the WMAP data. And then if we plot this, that's just a scatter plot, so this plots pixels in the model map against pixels in the WMAP data. And this is the synchrotron case, and you can see quite good correlation between the templates and the WMAP data.
So why is the map is squared or negative? That's what you asked. There's microterm is squared, but there are negative numbers on there. So how do we read negative squared?
Oh, this should be microcode. Okay, so to conclude, going to look at the foreground levels in patches being targeted by various suborbital experiments. And hopefully in the future we'll be using the model to constrain galactic magnetic field models. We're going to look at including small-scale dust density and correlating it with the small-scale magnetic field, and also Monte Carlo studies of the small-scale turbulent field to improve predictions on smaller scales. And the templates will be available for download here. The dust templates are already up there, but the synchrotron ones will be added soon. And for more details on either on the synchrotron model, you can look at this paper, and the dust case you can look at this paper here. Thanks for listening.
Does anybody have any more questions for Caroline? Ready?
I thought there are polarization maps from the Bonnie group. I thought has these, and also Parks has this S Parks or something, polarized survey as well.
Parks goes into the house.
No, that's the old property, like that's the ancient Parks there. But the more recently, there's been the S Parks, which is a higher resolution. I think S band, which was gigahertz. Polarimetric survey, which
2 gigahertz.
I'm not sure. S band.
I have no idea.
What the S band?
Used to be earlier, right?
That would be pretty cramped, right? 2 gigahertz. Wow.
Synchrotron, we can put that.
If you didn't model the polarization foregrounds, what would that do to change the accuracy of your measurement models?
Can't think of any specific cases, but I know that this paper by Untitled Chapter looked at various cases for including things like anomalous micro emission and looking at the biases on R from not including certain components. So I can't remember any of their conclusions, but I can look it up.
But I mean, can you roughly beat down the error bar by a factor of 2, or can you like more than that, or by doing this?
I know that doing this improves the constraints on our massively, but I can't say it.
When the Planck temperature maps come out, which should be like February, how much will using those as your intensity maps allow you to improve this model?
I think we would like to use that when it is available. Yeah.
Should be February, and like it. Since your Planck has, I guess Planck will give you total intensity maps at higher resolution than you actually need for your spider from Stokes.
Would be very interesting to update.
Does anyone else have any further questions? Okay, well, we'll go upstairs in a minute for cookies as usual, and we'll be going out for dinner